Good evening. My name is Meghla Krishnamurthy, and I am a member of the faculty at Ashoka University, where I teach sociology and anthropology. On behalf of Ashoka University, it gives me great pleasure to welcome you to Beyond the Classroom, our special series of live and interactive virtual seminars. This is our 9th session in a series where every Saturday and Wednesday at 8:30 p.m., we have a different member of the Ashoka faculty speak to us on a subject that they are passionate about and that matters deeply to their discipline. These seminars show us how and why each subject indeed matters for all of us and gives us an opportunity to open up a space for a wide-ranging interactive discussion with a diverse audience. Today, I am delighted to introduce you to our speaker for this evening, Maya Saran, who has been teaching mathematics at Ashoka since the university began in 2014. Maya earned her Ph.D. at the University of Illinois at Urbana-Champaign and conducted part of her graduate study as a research affiliate at the Massachusetts Institute of Technology. Her specialty is mathematical logic. Maya believes that there are many beautiful pieces of mathematics, like a great piece of art or music, that people don't know about, but that they can know about if it is just explained properly. And that is precisely what she will try to do today in a talk titled Questions Math Can't Answer. Hi, Maya.
Hi, Meghla. Thank you so much.
And hello to your magnificent bookshelf.
And to yours.
Yeah, it's so great to see you and really looking forward to this talk. But you know, when I saw the title, one of the things that struck me that it's not just a wonderful and intriguing title, but it's also such a self-confident title, right? I mean, most of the time our disciplines are called upon to constantly sort of explain our value, right? To surprise you with how much we can in fact reveal and how much insight we can have. So to actually lead with something like questions that math can't answer is quite extraordinary and wonderful. But also it just struck me that it's actually the way to think about the strength of disciplines, right? Not the weakness, but that it's when you see the limitations or what you can't, that you can actually figure out all the possibilities.
Yes, and make sense of what can be done.
Yeah, no, exactly.
Yeah, yes, absolutely. And I mean, for me, this is, like a very fun and wonderful opportunity to be able to speak about something like this. So it's true that math, people generally don't ask what is the point of math. They may or may not like it, but they will concede it has a point. It's the language of the universe, etc., etc. So, we don't, it's not a hard sell. But, one of the surprising things about mathematics is that it can't do everything. And that is it's an idea that turned mathematics on its head, actually. And so
no, I'm sure everybody, this just sounds fantastic. And I know that everybody is really looking forward to getting on and hearing the seminar. So I'm just going to give you two very quick points of housekeeping. The first is to say that Maya will speak for around 20 minutes, after which you can have send her your questions through the Q&A function on Zoom. You may ask the questions anonymously, or you can send in your name. That is up to you. All the seminars are being recorded and they will be put on our website. We will share the link for the entire series with you shortly. And that's it. So without any further ado, thank you so much for joining us for Beyond the Classroom. And I will turn over the screen to Maya Saran.
Thank you, Meghla. So welcome, everybody. And as I was just saying to Meghla, this is just fun for me. And I've always been interested in foundational issues in mathematics. Even as an undergraduate, I would read the chapter 0 of books to, where I thought about what are we really doing here? So I got a chance to see some of that in graduate school. And I just happened to, fall into mathematics. And I mean, I think math is where I belong. And I say this as somebody who struggled with it in school. I mean, math has strong reactions from many people, and often the strong reaction is, well, thank God we're done with that. But anyway, for this talk, you don't need any technical background, and I hope to be able to show you one of the landmarks of human intellectual history, really. People don't know about it, but it's an idea that turned mathematics on its head. And so maybe we should know about it. All right, so I'm going to share my screen here. Just a second. Okay, sorry, that went to the back. Just give me a moment. Okay, so the title of this talk is Questions Math Can't Answer. The talk is really about a theorem called Gödel's Incompleteness Theorem. So here we go. Hope you can see that. And the outline for this talk, I'm going to start by talking about the natural numbers and a question about them, and then discuss the idea of proof, which is the central idea of how mathematics is done today. Then I'm going to go into Gödel's theorem and Gödel's incompleteness theorem. And then I'm going to talk about what that means for our pursuit of truth. So that sounds grand, and it sounds grand because it actually is grand. Okay, so let's start with the natural numbers and a question. The natural numbers are where we start, and in two senses, Historically, this is where mathematics began in Mesopotamia and in Egypt with the natural numbers. And this is also where we start as children, and even very young infants seem to have a sense of number. They know that 2-ness is different from 3-ness. This is well before they're verbal. So these numbers are really natural in many senses. We start with these and their basic arithmetic, by which I just mean plus and times. Really not much more than that is needed. And then we can start thinking about them. So we've been playing around with these numbers for a very long time. And we build them up, we break them down. That's what you do when you play with things. And let's look at what happens if we break down a number using multiplication. So let's start with a number. Here's 60. We can break it down. It's 12 times 5. You can break it down again. And then finally, when you reach 2 times 2 times 3 times 5, you can't break it down anymore. We can try a couple of others. 33, you can break it down once. The game ends after one move. 17, you can't make any moves. The game is over right away. So now these guys that you get at the end, these are called prime numbers. These are the numbers you cannot break down anymore. So now, here's the question. Can you write some numbers down as a sum of 2 primes? So this just, addition. So let's look at 4. 1 is not a prime, by the way, and I've given a list of primes here just for reference. 4 is 2 plus 2. So yeah, the answer here is yes. 6 is 3 plus 3. You're allowed to repeat 3 and 3. 8 is 3 plus 5. 10 can be done in 2 ways, 3 plus 7 or 5 plus 5. And you may notice that on the left here, I've got all the even numbers going. So let's see how far we can take this. So here, you try these. I give you a second. 20, 26, 30, just 3 random even numbers. Can you express them as the sum of 2 primes? And it turns out that you can, and here is a way to do it for these 3. So, okay, we didn't try very many, but we could do it every time. And the question is, does this always work? So Christian Goldbach in 1742 said, yes, it always works. And this statement is known as Goldbach's conjecture. So here it is. Any even number after 2 doesn't count. Any even number after 2 is the sum of 2 primes. He said that this is the case. Now, it's a conjecture because we don't know for sure. 1742 is a long time ago. And you might wonder, well, that was a long time ago. Didn't we have enough time just to check? Can't we just check? We can't check because this is a statement about all even numbers. And there are too many to check. How many are you going to check? There will always be more. We actually have checked up to 4 billion billion. 4 billion billion is an even number. Every even number up to this point, we have checked is the sum of 2 primes, but we still don't know whether this holds for every even number. So this problem has been around for so long that it's made it to the Guinness Book of World Records. It's the longest standing maths problem current. So Fermat's last theorem, another famous theorem, stood for longer than this. It stood for, I think, over 350 years, but it's now solved. So the current record holder is Goldbachs conjecture. All right, so let's think about it. How would we establish the truth or falsity of this statement? Any even number greater than 2 is the sum of 2 primes. So here's the statement for us to look at. To show that it's false, a single counterexample will suffice. So if you are able to produce just one even number, it will be a big one because we've already checked a lot. Just one even number and show that, look, this guy can't be written as the sum of 2 primes. Then we're done. The question is settled and it is false. But how would we show that it's true? Now, examples are not enough. We need an argument. We need to show a reason, an explanation of why it is true. And when we have an explanation of why it is true, that's exactly when we know that it actually is true. So the two are the same, seeing why it's true, being convinced that it is true, and knowing that it is true. These are the same thing. All right. So let's think about this idea of proof. So this idea of proof that we work with today, it goes back to the Greeks. So if you were receiving an education in a classical education in ancient Greece, you would study rhetoric, logic, and grammar as part of your education. And it was very important for them to have discussions. Rhetoric was an important subject. You have to be able to have a meaningful, intelligent discussion and convince other people of something. It's not random talking. They thought a lot about what does it mean to think properly? What does it mean to have an inference that actually makes sense? If you say something, you have to justify on what basis you're saying it. So this has nothing to do with mathematics. This is just about an argument. How do you make an argument for something? So how do I prove something to you? How do I persuade you of something? We start with things we agree on. That's our starting point. And then we have a process of reasoning that we both follow, like we have to both be on board with these things, the basic things we agree on and how we reason. And then hopefully this process of reasoning brings us to conclusions that we also agree on. So the idea is that if you agree on a set of initial things and you have faith, mutual faith in the process of reasoning, then you will also agree on the conclusions. Now, what goes in this first box over here? Things we agree on. Turns out we don't actually agree on much. What are the things we all believe? What are the things that are obviously true to us? Here we want to put small things, obvious things. So we won't put a big statement like, you know, democracy is the best form of governance. That won't go in the first box. Maybe in the first box, we'll have something like people have a right to be happy, or people want to be happy. Something that we believe and that is obviously true to us, the starting point of our discussions. Now for mathematical reasoning, here's a question. Do we even need anything in the first box? So if you are a graduate student and you're taking your first course in mathematical logic, let's say, we won't say who this is, but maybe you think, let's develop math from pure thought. We will assume nothing. This is a kind of exciting goal. So you have stars in your eyes and you want to develop math from pure thought and assume nothing. But if you assume nothing, you actually can't conclude anything. If the first box is empty, there are no assumptions, what are you going to base your reasoning on? You do need something in the first box. All right, so we need something in the first box. Now, for a long time, people did arithmetic and thought about the natural numbers without worrying too much about what was in the first box, because it turns out that there's a lot of small facts about the natural numbers that are obvious to us. But a series of mathematical developments in the 1800s led mathematicians, a number of mathematicians, to think hard about what goes or should go or what we want to go in that first box. What is the starting point of our reasoning about mathematics? Whatever it is, we want it to be simple and minimal. So here's one attempt. Peano's axioms, he was an Italian, for the natural numbers. This was his proposal. Let's put these things in that first box for the natural numbers. This was in 1889. The first axiom or assumption, obvious truth, is that, look, there is some natural number. There is something. And let's call it 0. Excuse me. And then we also assume that every natural number has a successor. There's always a next one. So 0 plus 1 gives you 1, then 1 plus 2 gives you 2. You can keep going. There's always a successor. There is no end. And the third one is that, look, everything has a successor, and many things are the successor of something else, but not 0. 0 is the starting point. It is not itself the successor of any natural number. It's really small facts about the natural numbers. And then the fourth and the fifth. The fourth one says that, well, if two things have the same successor, they were the same to begin with. So if a plus 1 is equal to b plus 1, then a is equal to b to start with. And then the last one says that if you have a collection of natural numbers and 0 is in there, and the successor of 0 is in there, and the successor of that is in there, and so on, then in fact, all the natural numbers end up in that set. So this is called induction. Anyway, this is it. That's it. A short list. And we can agree, or we can agree to agree, that these are simple, they're obvious, they do reflect truths about the natural numbers. And based on this starting set, this first box of ours, we can start proving things. And it turns out that Peano's axioms are sufficient to prove lots of very rich, complex mathematics. But it turns out that we want more than just simplicity. So here is our wish list, ideal wish list for a set of axioms. We want the axioms, the things that go in that first box, we want them to be consistent. So that means whatever happens, it doesn't lead us into contradiction. So we put a bunch of axioms at our disposal. We start proving things. We don't want that, one day I'm able to prove a statement, and then the next day I'm able to prove the opposite of that statement from the same set of axioms. That would mean that my being able to prove things doesn't mean anything. So that we don't want that. We want our set of axioms to be consistent. And then we also want it to be complete. So what does completeness mean? You should have enough things in your arsenal of axioms. You should have put in enough things there that allow you to determine the truth or falsity of any statement. So if I ask anything about, let's say, the natural numbers, I ask any question about them, for example, Goldbachs conjecture. Is it true that any even number greater than 2 can be written as the sum of 2 primes? Well, there should be a way to settle it. Either it's true, or either I can prove that it's true from these axioms, or from the same axioms, I can prove that it's false. This is a feature of the system that I want. I want to have put in axioms in the first box, which give me something that's consistent, doesn't lead to contradictions, is complete, and which means it should be able to settle every question. And finally, I don't want like a rubbish baby system that can't actually do very much. So I can just put in Peano's first axiom. I can say, all right, there is a number 0. That's it. Stop there. I'm not going to put in any other axioms. maybe because I'm worried about spoiling consistency. Okay, fine, but that's not going to allow me to establish even basic arithmetic. I need my system not to be too weak. I want it to be a useful system. So this is the wish list, these three things. All right. So here's David Hilbert. He was a German mathematician. And in the year 1900 in Paris, there was an international Congress of mathematicians. And at this meeting, Hilbert gave a very famous lecture in which he gave a list of 23 problems that he thought were the most important agenda-setting problems of mathematics that mathematicians should focus on. And the second of those was this: let's come up with a bunch of axioms that meets this wish list. And he was ambitious. He wanted this to be done for all of mathematics, a small set of axioms, reasonable axioms that meets all our requirements. It should be consistent, complete, and sufficiently strong. And he said, okay, everybody get to it. Let's do this. Okay, so one of the people who got to it, who said, okay, fine, let's do it. He was interested in Hilbert's program and he wanted to contribute to it, was Kurt Gödel. And that brings us to Gödel's theorem. So here he is, this is Kurt Gödel. So you know who the other guy is, of course, it's Einstein. And this is a picture of Gödel and Einstein at the Institute for Advanced Studies in Princeton. So Gödel was much younger, as you can see, and he arrived when Einstein was already there. He was Austrian. He was an Austrian mathematician, and he was part of the wave of mathematicians that came from Europe to the US around that time. And here are the two of them. They used to walk to and from the institute together, and they were fast friends. Somebody else at the institute, somebody called Borel, said of them, they didn't want to speak to anybody else. And Einstein has said he went to the Institute for Advanced Study just to have the privilege of walking home with Kurt Gödel. Now, one of the reasons he enjoyed his company was that Gödel didn't care that he was Einstein and would challenge him on his ideas. So both of these figures, Einstein and Gödel, changed the way we think about each of their fields. Einstein did it for physics and Gödel did it for mathematics. So they addressed the big questions, the foundational questions, and both were interested in finding out what is true. Einstein about the physical world and Gödel about the abstract world of mathematics. So another thing that they both shared was a common belief in the nature of reality, which many people around them actually didn't share. So I'll say more about that later. So here are Einstein and Gödel. This is a famous friendship. So what did Gödel say? He said, okay, you want a nice set of axioms that meets your wish list. It should be consistent, no contradictions, complete, that means it can settle every question, and strong enough for basic arithmetic. That's what you want? Well, it's not gonna happen. Any consistent set of axioms that accomplishes basic arithmetic is never complete. He's not saying it may or may not be complete. He's saying it's definitely not complete. You can't have all your wishes come true. You can have two, but then the third one is forced to not work. So this theorem is called Gödel's incompleteness theorem. So here's one way to look at it. Suppose you have an oracle and you feed into the oracle, you tell the oracle, look, these are my axioms. I'm telling you what the axioms are. It could be a computer or an oracle, doesn't matter. You feed in the axioms and you also explain to the oracle what is your proof process, what is the method of proof. So the oracle or the computer, it knows what the axioms are and it knows how to carry out proofs. And then you want to be able to ask your oracle for any statement, is this statement true or false? And the oracle should say true, or maybe if it's false, the oracle will say false. So the ideal oracle would be able to answer every question. Once you fed in the axiom, and it's too much trouble for me to carry out the proof, okay? So you do it, let the machine do it, let the oracle do it. I just want to ask, is every statement true or false? And the oracle is capable of every proof, however difficult. It will tell me is true or is false. It will settle it on the basis of the axioms. But incompleteness says that on some questions, the oracle will be silent. Not because it doesn't know how to do proofs, because there is no way, there is no proof of the truth or of the falsity of those questions. So there will be some statements that escape your net of proof, no matter how you have set it up. You can set it up differently, but then there will be new questions that escape that net. So he proved this. Now, how did he do that? We know how to prove things about numbers. How the heck do you prove things about statements? So let's look a little bit, just for a minute, about how he did that. And his genius idea was something called the arithmetization of syntax. So this is how it goes. The idea is actually very simple. I mean, really, we've done it all as children when we played Spy is Spies. He turned statements into numbers through a system of coding. Now, suppose you want to turn an English statement into a single number. It could be an English statement expressing something about mathematics, whatever. All right. So here's one way to do it. You assign each letter a number. So A is 1, B is 2. Okay, we're not being very imaginative. Z is 26, and then space can be 27. All right. Now you take a sentence like this, see you soon. It becomes a sequence of numbers, but we want to churn out one number, not a sequence of numbers. So we can put zeros in the middle, and here, this one sentence becomes one number. All right, it's a big number, but whatever, it is a single number. So in this way, you can make a correspondence between statements and numbers. And a proof is also a sequence of statements. And in a similar manner, you can crunch down a whole proof, a whole sequence of statements into one single number. So you give me a proof, I'll crunch it up and wrap it up and give you one single number. This proof has turned into this number. And I can unpack it as well. If you give me a number that represents a proof, I can unpack it and see the proof again. So this was the main idea. Now, this doesn't seem so genius by itself, but look what happens. Something like this statement is a statement about statements. There is a statement such that there is no proof of its truth and also no proof of its falsity. This can be translated via the coding into a statement about numbers in the following way. It becomes there is a statement number instead of statement. It gets replaced with statement number, such that there is no proof number for its truth and also no proof number for its falsity. And now showing that a system is incomplete becomes a matter of showing there is a number with a certain numerical property. And that is how Gödel proved his statement of incompleteness, by translating everything, the statement about statements, into something about numbers, which he was able to prove. So let's see, what have we done? Our goal was to determine all truths about the natural numbers. This is a goal. The method is you start with obvious truth, axioms, and reason out the rest. The question is, what should go in that list of axioms? This is Hilbert's question. And the dream is find a perfect list that will never lead us into contradiction and will settle every question. And then Gödel comes along and he shatters that dream. He says, well, it's not possible. You can stop trying. It's not possible. All right. So this really changed people's view of what mathematics was about, how it's done, what is it capable of. And it certainly put the last nail in the coffin of Hilbert's program, at least in the form that he had stated it in. So now, what does that mean for our pursuit of truth? Suppose we go back to Goldbachs' conjecture. Maybe there's a proof we haven't found yet. Maybe there is a proof, maybe it's true, and we just haven't been smart enough or, creative enough to find a proof, but there is one. Or maybe it's an escapee statement. It's possible that it's one of those things that escapes the net. It can't be settled using our standard axioms. And if it is an escapee, if it is secretly a statement that is not capable of being settled by our axioms, we can't prove it's true, and we also can't prove that it's false in that case. So does that mean it's neither true nor false? So this is something worth thinking about. I mean, somehow we feel when we think about the natural numbers, there's 1, there's 2, there's 3, there's 4, think about the evens, 4, 6, 8, 10, etc. Keep going. And you have a feeling that either there is some even number that can't be expressed as the sum of 2 primes, or there isn't. Either there is or there isn't. And if you agree with this, then you are a Platonist. And Gödel himself was a Platonist. He said the Platonistic view is the only one tenable. He believed that mathematical objects have a real existence independent of our minds. Whether or not we think about them, whether or not we can figure them out, they are there. And there are things that are true of them, and there are things that are false of them. So this is what he shared with Einstein. Einstein, this is a quote, he says, out yonder, there was this huge world which exists independently of us human beings and which stands before us like a great eternal riddle, at least partially accessible to our inspection and thinking. And he says the contemplation of this world beckons like a liberation. This is something he said on the occasion of his 70th birthday. And that's why beckoned is in the past tense. But this is a view of reality that Einstein and Yodels shared. And other physicists and philosophers of the day did not agree at all. Heisenberg, for example, was of completely the opposite view of Einstein. But they both believed that there is a reality, a physical or a mathematical reality out there that exists independent of our thinking about it. There is a 2, there is a 3, there are these things out there. They're not just in our minds. So his own conclusion, Gödel's own conclusion was that, look, you might have an oracle like this, but it's answering questions on the basis of their provability. But provability is different from truth. So the incomplete nature of any proof system doesn't mean that mathematical truth can't be determined and is not worth pursuing, but it does mean that a mechanical approach to mathematical truth is never going to work. There will be room for the human mind, the human consciousness, and creativity to examine whether something is true or not, even if there isn't a proof of it according to some particular axiom system. I'm going to end with a picture of Hilbert's grave. This is his grave somewhere in Germany. And at the bottom, it says, "Wir müssen wissen, wir werden wissen." It's a testament to the human spirit. We just want to know, like, who cares about Goldbachs' conjecture? We checked it till 4 billion, and after that, who cares? Like, why would we spend, 200, 300 years thinking about it? Well, one of the reasons is it's an interesting mathematical question, okay, but also we just want to know. It bugs us that we don't know. It's like a puzzle. We want to know. And so Hilbert's grave has this inscribed in stone: we must know, we will know. Okay, thank you. Thank you. I'm going to stop here. And I'd now like to welcome my student and ask her to join us, Saloni Mehta. She is a student at Ashoka one of my students, a major in mathematics, and she is also completing a minor in performing arts and computer science. So nice to see you, Saloni. Thanks for joining.
Hello.
She's going to help us. Saloni is going to help us go through some of the questions that have been coming in.
Before we begin with the questions, I'd just like to say this entire talk was so great, and it just took me throughout the trajectory of my math education at Ashoka, starting with natural numbers and then, decimals and then reals and everything else, and how much of human spirit and effort goes into making mathematics. Right.
Yeah, that's true. That's true.
So we will begin with the questions.
Yeah, sure.
Right. We've gotten a lot of questions. We've gotten a lot of questions.
Okay.
So what we'll try and do is we'll collate the common themes and try to address them first. And we'll try to go through as many questions as possible. So the first question is by Bharat Gangwani. He asks, early mathematicians were also philosophers. Could you elaborate on how the two complement each other, especially with your background in formal logic?
Yes. Okay. So I get this question a lot, the connection between math and philosophy. And, there is a philosophy of mathematics. You can think about in philosophical terms, what are mathematicians doing? What is the nature of mathematical truth? These are interesting philosophical questions. But at the same time, most working mathematicians never think about these things. They don't wake up in the morning and say, okay, what is the nature of mathematical truth? They just prove theorems. And, the amazing fact is it's really mind-boggling. It works. It works. I mean, I don't know if natural numbers are out there or just in our heads or what, I don't know. Like real numbers, are they a thing? They're so complicated and we've made it so abstract. Are they really a thing? I don't know. But when we use this theory and we, do some calculations and we send a rocket to the moon, like we point it in this direction and we make it go off like this, and 4 days later it lands on the moon. So we've got something right. And most mathematicians don't think too much about these things. The practice of math is not really affected much by these questions, although of course there are some people whose job it is to look exactly at these questions. Yeah.
Great. We'll move on to the second question. This is an anonymous question.
Mm-hmm.
If Goldbach couldn't prove his theorem / conjecture, how did he develop this in the first place?
Yes. I'm not sure about the answer to that question, but that is a very good question. How do conjectures come up? So there are some conjectures that people working on something, they notice a pattern and they think, I think it's like that. I don't know exactly what he was working on when he came up with that. I'm not a number theorist, but it's often while working on something else, you notice something. So, George Cantor, when he came up with his notion of different infinities, this is another landmark of human history. He wasn't really thinking about these. He was thinking about something else. He was thinking about trigonometric series. But you notice something and you conjecture something, it seems true to you. Some mathematicians like Ramanujan, they just dream up truths, but most people are working on something and they notice a pattern and they conjecture that it's true. And also, if you're an experienced mathematician, you have a sense of things. And you may be wrong, of course, but you have strong intuitions about the truth or falsity of things.
Right. This is also what happens when you're an undergrad trying to solve math. You'll be showering and you'll be like, okay, question 5, this is going to be my answer. You run out and I'm going to jot this down before I forget it.
Yeah, exactly. Yeah. And it didn't fall from the sky. I mean, you sowed those seeds and watered them by thinking about them, and then, some neurons fired and then you have it, but you needed that initial time. Yeah.
Right. Our next question is very interesting. Malini asks, is there a method to find out if a statement is one which is beyond the scope of our axioms and cannot be proved true or false? That is, it's an escapee statement. And can there ever be such a method?
That is an excellent question. No, the answer is no. I mean, if we had such a method, life would be easy, right? For example, Goldbachs conjecture. We don't even know whether we should, like, it's an escapee statement, it's independent of our axioms. And so we should just, stop trying to find a proof and think about it in some other way. We don't know. So no, the answer is that there isn't. Yeah.
Right. The next question is by Ananya. She asks, she starts with, pardon me if my question sounds ignorant. I'm a student of economics. What I wanted to know is, what do you mean by using maths to look for the truth? Truth about numbers or about the nature of reality or consciousness?
Yeah, no, we, just do math about abstract, or we prove things about abstract object. Yes, numbers in short. Yes, numbers. But even there, 6 plus 7 is equal to 7 plus 6. Is this true? Yeah, it's true. But where is it true? Like, what is the nature of this truth? What are these things? Is there a 6? We call them natural, and they're natural to us, but do they exist in nature? I mean, there's 6-ness, there's 2-ness, and we seem to just understand that without like having to mess around too much with too many words. We get it, 2-ness, but is there a 2? So yeah, I don't know, but yes, it's about numbers, whatever they are. So mathematicians do this thing. You can think of it as genius, or you can think of it as cheating. They say, well, whatever. If there are some objects which have these properties, then about those objects, we can say these further things. And they don't worry about whether what they are talking about exists or corresponds to some reality, even though secretly we know it probably does correspond to some reality. And the universe seems to know what we are doing, and we are able to make predictions about the physical universe based on these sort of man-made entities called numbers. So maybe they're not really man-made. Yeah. Well, that's just how it is. Yeah.
Right. The next question is a really fiery question, and it comes from Dean Raja. And he asks,
hi, Raja.
If probability and truth come apart, is the assumption that Platonism is the only option to accommodate this?
Right. Okay. So now, do probability and truth come apart? Well, probability, at least with respect to Gödel's theorem, is about probability with respect to a certain particular axiom system. And if we think of it in terms of models, if something is not provable from an axiom system, for example, there's a very famous problem called the continuum hypothesis. It was a conjecture about the sizes of certain sets, subsets of the real numbers. This has turned out to be not provable from our standard axioms, but somehow, we can still think about it. We can still think about its truth. So do provability and truth come apart? The statement is very grand. Technically, they come apart with respect to a particular axiom system only. So if you stop being grand and just look at it as a technical result, these questions sort of go away. So, Raja, I don't know if this is a satisfactory answer, but we can talk about it later.
Right. I just want to remark here, the faculty discussions at Ashoka are exactly like this. I remember Professor Raja coming into maths colloquia and asking these sort of questions, and me just sitting there bewildered. So I think this is great, especially when there's such banter here. The next question I wonder is from a certain Hari Hari.
Okay.
They ask, why is there an assumption of existing truths in mathematics and physics? Why isn't falsity assumed?
Okay, so let me see if I understand that question. It's like this. You want to study some objects. This is our starting point. There's something we want to investigate. If you're a physicist, it's maybe the universe, the physical universe. If you're a mathematician, it's mathematical objects, whatever they are. We don't even have to like say, well, are they real? Where do they exist? Blah, blah, blah. They're a thing. We say they're a thing, and we want to study them. And the physical universe seems to obey the laws that we have come up with. So they're worth studying. So some things are true about these numbers or objects or whatever you're interested in, and some things are false. We actually are interested in both. What are the things that are true and what are the things that are false? If we want to investigate all possible truths about this system, we'll start with some small obvious truths and then go from there and figure out what else is true and also what else is false. Yeah, but you can play around with axioms. I mean, you can play it as a game. Well, what if this axiom is false? You are allowed to assume whatever you want and then go from there. But we don't want to waste our time. It's not just a game we're playing with symbols. We are actually trying to figure out the nature of something. And so we want to feel our way through to something that, some statements that are true of those entities. And that's where we start. Yeah. But when you say some things are true, you are sifting, you're deciding, okay, these are the things are false, we'll take these. So we do think about falsity, very much so.
This reminds me of that saying, it would have been great if life was as sorted as math was, relating to the assumption. We're very clear on the assumptions we make. Right.
Yeah, it's true.
The next question is quite interesting. Karthik asks, is math discovered? As in, is there a mathematical essence to the universe? Or is math just a creation of our brains?
That depends on your point of view. But does it matter? It's an interesting question. Yes, but really, I mean, I've, like I said before, like, is there a 6? Did we discover 1, 2, 3, 4, etc., or were they already there? Were they given to us by God? What about the real numbers? I mean, they have a very technical definition, but they also have a simple one. All the points on a line. Root 2. Where does this exist? I don't know. Does it exist, and did we discover its existence? Or did we invent something that we call root 2? I don't know. But that doesn't stop us from thinking about root 2 and saying things about it. So it depends on your point of view. You can make a case either way. It doesn't affect the practice of mathematics.
Right. So the next question is, I think, a very important question as well. Dhaval asks, is language or principles of mathematics same in different cultures or languages?
Okay, I would say the answer is basically yes. So not all cultures pursued mathematics in the same way and in the same to the same extent, but those that did came up with the same thing in different periods of time and different geographical locations. There are things that Ramanujan, for example, we all know about Ramanujan, that he discovered by himself sitting in his room because he was cut off from the rest of the mathematical world to a great extent. But they were already known. He rediscovered them. This happens. It happens. Maybe that's not a good example because he was very much speaking the same mathematical language. But yeah, I think my answer to that is yes. we can ask Mekla afterwards what she thinks.
Right. I've often had this discussion with other people. What is the socio-cultural context of numbers? Are numbers just mechanical? But I've always felt there's such human effort and human spirit that goes into making math. You cannot isolate math. Like,
yeah, absolutely. It's a very human discipline. It absolutely is. You know, who else would like want to think about something for like so long and spend, you know, lifetimes just collectively and also individually, just thinking about some problem. Like we just want to know. That is deeply human. Yes, and turns out that many of us thinking about this come up with the same thing. We seem to be onto something. It works, you know, like, I don't know, you pick up your phone, you dial a number and then it all works, and it's all been worked out with mathematics. It's working. We seem to be onto something. It's called the unreasonable effectiveness of mathematics. This is what it's called. Yeah.
right. So we'll move on to the next question.
Yeah.
Josh asks, does Gödel's theorem find application beyond mathematical systems?
Well, it is a technical result. And it gives the answer to a particular question. Is it possible to find a set of axioms that does blah, blah, blah? So the immediate answer is no. It is a technical result in meta-mathematics, which is proved using the methods of mathematics. Now, what does it imply for the nature of truth, for how we get knowledge? These are questions that it might be able to inform, but at heart, it is a technical result. It did change the way we think about mathematics and mathematical truth, but again, it's with respect to a particular axiom system. You can change it. And so we do think about changing it. You know, there are papers written about, well, is it time for a new set of axioms in mathematics? We are still thinking about it. We have to make choices. And the choices we make determine what are the things that we will or will not be able to say. Something will always escape. Okay. Yeah, no, it's a technical result about mathematics, basically. Yeah.
Right. So this is a question I want to slip in and ask
yes,
you.
You'd get to do that.
Yes. So my question is does the inverse of the theorem hold? Which is to say, will a complete set of axioms be not consistent?
Okay, so there's this other part about being strong enough to model arithmetic. Yes, there are complete and consistent sets of axioms, but they will not do arithmetic. They will not be supersets of the piano axioms, for example. If you want piano's axioms in there, this basic sort of core set, then you can't have consistency and completeness together. Yeah, you can have one or the other. Yeah. Okay, good question. All right.
Right. The next question is slightly longer. Atmesh asks, if only one counterexample is needed to disprove a statement, then does that mean that all statements have the potential to be disproved? Assuming we are just near finding the counterexample.
Yeah, yes. A statement of this kind, a statement of this form about every natural number. Every natural number has a certain property. To disprove this, you just need one natural number to not have that property. And you can start looking. You can set a computer to look. But the thing is, often the number of computations required is so high. Well, there are two issues. One is that you're constrained by like the physical computing needs. It takes time and energy and all of that. The other is that even if you let your program run for 100 million years, you're never going to get through all the natural numbers. So yeah, but in theory, yes. Yes. If the statement of this kind is false, then yeah, you could just start looking. But the thing is, you don't know whether it's false. Maybe it's actually true. So all this looking is wasted. Yes, but yes.
Okay. This question is anonymous. What major changes have taken in the nature of math research over the years due to the onset of modern computing?
Yeah, that is an excellent question. So there are theorems that have been proved on the basis of somebody having checked a whole bunch of things by using a computer that you could never have checked by hand. And the famous and first example of this is the four-color theorem. If you take a map, just like a map of countries or states or a paper, like literally a map, and you want to color it. And the rule is that two states or countries that share a border should not get the same color. You can do it with four colors. You never need more than four. If somebody gives you four color pencils, say, I can't give you more, now go do the job, you can do it. Might take some figuring out, but it can be done. So this is called the four-color theorem. And this is the first example of a theorem that was proved using computers. Now, do you think that is a valid proof? If a proof is supposed to persuade you, and you said, oh yeah, I checked it on a computer, are you actually going to persuade anybody? This is up for debate. It's accepted as a theorem, it is. But do we want to consider that a proof? We have to decide. We may decide in some cases, we decide on a case-by-case basis. Yeah, this one we accept, but some other ones is too much to accept. The black box is too big, and we may not want to accept it. Yeah.
I think this is also where the humanness of the discipline comes in. You have to move me by your proof. You have to persuade me. Nothing can oblige me to say okay to your proof.
Yes, true. Except you yourself being convinced. When you are convinced yourself, based on my arguments or based on whatever, you will accept it when you are convinced, and you shouldn't accept it before. Yeah.
Right. So this is the last question, Maya.
Yeah, sure.
And the question asks, so many people are afraid of maths. What advice would you give to them?
Oh, gosh. Math in school is taught in a way that is very much focused on like the execution of algorithms and a lot of drills. When you're 5 years old, you're learning algorithms to add things. You write this number, underneath you write this other number, then you do this, and that's addition. And now you please do 1,000 of these until you become very good and get the right answer every time in 2 minutes, or like much less than 2 minutes. And then when you're in class 12, it's the same thing. Okay, this is how you do integration by parts. This is U, this is V, blah, blah, blah. This is how it works. Now do 1,000 of these until you get really good at this. So I don't know if I can give you any advice, but I can say, that's not what math is about. That is, we think about ideas and structures and patterns, and we there's never any template that if you can figure something out in 2 minutes, that question is probably not worth thinking about. So I can just assure you that the kind of thing that you probably hate and probably are afraid of, that's not what contemporary math really is. So give it a chance. There are some nice books you can read. Maybe we're going to share an email with people who registered, and I'll put some of those in the emails. Reading suggestions for people who are recovering from bad experiences with math. I'm one of them. I failed math in class 11. I passed into class 12 with grace marks, 2 grace marks. It wasn't fun. And, that's how it is. It didn't mean anything, those bad marks. Yeah.
When you do enter college, you're like, okay, college math is very different from what school math was. And if anyone's interested in looking into what college math is, go check out math at Ashoka page. You will be really, really smitten by what's there. Well, that's it for today. Thank you so much, Professor, for this wonderful, wonderful talk. I hope you really enjoyed this.
I did. This is like, as I said, this is like a dream. Like you get to talk to so many people about this amazing thing. Yeah, everybody knows about Einstein. Why don't people know about Gödel? It's because Gödel is part of mathematics and people are afraid of mathematics. It's a closed door. So, but it has like a very like human, wonderful history, and it's how we have a lot of things have been figured out within and through mathematics. So I hope people got a glimpse of that. Thank you, Saloni, and thank you to everybody for logging on and watching. Thank you. Bye.
Thank you. On behalf of Ashoka University, thank you to all our participants for joining us in the 9th seminar of Beyond the Classroom. And thank you for sending in all your questions and comments. We would love to get your feedback on this seminar. And in fact, right after it ends, there will be a 30-second survey that will pop up on your screens. Please take the survey and tell us what you think. Keep a lookout in your inbox. We will be sending you a follow-up email with additional readings and the seminar recording, including what Professor mentioned today. Finally, I would like to remind you that we have a new faculty member and topic every Wednesday and Saturday evening at 8:30 p.m. Follow us on Facebook and Instagram for the topic, faculty member, and sign-up details. Have a good night and see you on Wednesday beyond the classroom.